speaker. So our next speaker will be Dr. Saptarshi Debroy. So are you here? Okay.
Yes. Can you hear me?
Yes. Let me introduce you first. So Professor Saptarshi Debroy is the assistant professor of computer science at Hunter College and a member of the doctoral faculty at the Graduate Center of the City University of New York, CUNY. At CUNY, he is the founder and the director of the Distributed Security and Resource Management Lab. Before joining CUNY, he was a postdoctoral fellow at the University of Minnesota, Columbia. He received his PhD degree from University of Central Florida in 2014, master degree from the Jadavpur University, India in 2008, and the bachelor degree from the West Bengal University of the Technology, India in 2006. His current research interests include cyber security, distributed and cloud computing, big networking, and wireless networks. His research accomplishments include NSF Early Career Award, being nominated for Presidential Early Career Award for Scientists and Engineers, multiple Best Paper Award, and winning the gold medal for research at Jadavpur University, India. He is a member of ACM and IEEE. So now the stage is yours.
Thank you so much, and thank you to the organizers, and especially Zheng Yu for inviting me. So it's can you see my presentation? Can you see my presentation?
Yes, we can see that.
Okay, perfect. So it's a talk fast to follow up after this. This is such a great talk. So what I'll try to do is because it's 4:30 already in East Coast, so I'll try to keep it a little high level, and hopefully I'm able to generate some interest in my research. So hello everyone, I'm Saptarshi Debroy from Hunter College and the Graduate Center of City University of New York. So this is a work, I won't say this is a work because this is just the starting point of the work that we are doing at CUNY. So the title of the talk is Mobile Edge Resource Management for Future Smart Disaster Response, Challenges and Direction. So this is kind of outlines the NSF Career Award that I just received in 2020. What are the different challenges that I'm looking at, and what are the different avenues that I'm exploring. So this is partly in collaboration with the Fire Department of New York, and so let's see. So smart disaster response, the proposals that we see in academia, and also some of the proposals that we see from the first responders coming up are mostly cloud-based. So in cloud-based system, you have a device view, so device level where the first responders and the end user devices are at the same level. And then you, if you can do all the computations there at the device level, then you are looking at, say, around 1 milliseconds of end-to-end delay, which is pretty good, which is what the first responders need for real-time disaster response. But the problem is the devices themselves are energy and computation constrained. So another option is to go to the network edge. Some people call it edge computing. Some people call it network edge computing, because edge computing definition is kind of vague, I would say, still at this point. So if you are going to network edge, then you're looking at end-to-end delays around 10 milliseconds to 40 milliseconds, which is not really real time. And in disaster response, real time means actually saving lives and not being able to save lives. So in this context, real time should be real time. And especially if you're going to the cloud data center, then you're looking at more than 100 milliseconds, which is too far and too slow. So what we propose, so rather before we go to the proposal, the idea is how to provide near cloud scale resources, near cloud scale, because you can never provision cloud scale resources. But so idea is near cloud scale resources for mission critical real time application on premise. On premise means where the actual disaster has happened, closer to the first responders. So what we propose here is a smart disaster response, which is mobile edge computing or fog computing based. So you have the disaster like first responders here. You have the end devices, and then you have these multi-utility vehicles which can work as base stations, and they have the CPUs and GPUs to process these real-time workflows, real-time applications, and rapidly send the process data to the first responders for rapid response. So that is the idea. The question is, what are the challenges and what are the realities that are kind of impediment to realize this dream? So you have heterogeneous applications. These applications vary from object detection, 3D reconstruction, artificial intelligence, augmented reality, and again you have the applications of artificial intelligence. So you have inexpensive devices and you have multiple agencies. So imagine a disaster response scenario where you have the EMT involved, you have the fire department involved, the police department involved, and you are talking about a future which is not so far, where you have all these agencies running their own applications, they're competing for resources. So it's a heterogeneous application and a lot of chaos, frankly. And then you have heterogeneous requirements. So you have heterogeneity in terms of quality of service these applications require. You have energy. In terms of energy, you have diversity and heterogeneity, and you have reliability, because you need kind of 5G reliability or even more than 5G, which is 99.999% reliability. Then the environment is dynamic. So you're talking about a disaster environment. We have fluctuations of resources. If you are using dynamic spectrum access, you can have fluctuation of networks. So it's a chaotic environment. And on top of that, computational and energy constraints at the edge are constrained. So you have, it's not like cloud where you have unlimited energy and unlimited computation power. You're talking about on-premise edge. So in on-premise edge, even these multi-utility vehicles, these trucks, they have limited energy, right? It's much more than the devices, but you have to consider energy constraints and computation constraints when you are doing resource management. So one of the first applications we are looking at is real-time object and pose detection with mobile edge computing. So object detections are mostly used to identify whether there are human beings at a disaster site or whether there are pets on the disaster site. So pose detection for large-scale triage, so you want to figure out whether who are the people who are most vulnerable, who needs immediate assistance. So for those reasons, you have object detection and pose detection very relevant for disaster response. And mostly these applications are modeled as sporadic tasks. We're using like direct acyclic graphs, and these jobs have very strict processing and latency requirements. So that is the challenge, and that's why they are mission critical. And this and then these mobile devices have we talked about this before, like they are energy and computation constrained, so which intuitively leads to the task being offloaded to edge servers. So what you want is the devices to offload their tasks to the edge servers. The question is how difficult or how easy it is, and what are the different considerations we have to take. So this is a simple example or simple experiment that we ran. So it's an application implementation using Apache Storm. So there are 6 applications that we ran with multi-stage applications. You have some compression aspect, and then some YOLO computation with different resolutions. So the idea that we saw was like the transmission of data is considerable. So if you're talking about like wireless connectivity between the devices and the edge side, so the data transmission, that time might be considerable. And in some cases, we have seen that it is better to do some computation locally than offloading everything to the edge side. So in this example, you will see that so the application 6 here is like the entirety of the data is being transferred to the edge side. So the transmission time is pretty high, whereas we are looking at the transmission cost of applications where you're doing simple compression at the device side, which does not really take up a lot of device energy and computation, but you can significantly reduce the time to transfer the intermediate data. So sometimes it makes more sense to locally compute and then transmit the intermediate data rather than transferring all the raw data to the edge side. So based on that, we came up with a problem. Again, I'm not going to go into details of the problems and equation. I want to keep it interesting at kind of high level. So the idea that we proposed was a combination of a centralized resource allocation and a distributed resource allocation, which is more of a strategy making. Essentially, the centralized component wants to minimize the overall energy and also wants to delegate jobs based on resource availability. Whereas a distributed component, what it's trying to do is it's figuring out the best offloading strategy in terms of if you have a DAG, which part of the DAG should be done locally, which part of the DAG should be done at the edge site, based on minimizing individual energy consumption. So a combination of these two are giving us kind of a close to optimal solutions. So the outcome of the optimization would be application partitioning and task offloading. So you partition the DAG and then you figure out where do you want to do it, either server 1 or server 2, and where you do the cut, where you do the DAG cut. So these are the two things that we are considering. And hopefully this kind of generates an instruction level parallelism, which can bring down the overall end-to-end latency considerably. But the challenge remains is the synchronization, because you're talking about instruction level parallelism. So you have to have perfect synchronization. But the question is, can we do that synchronization on a large scale where there are a lot of applications involved, a lot of applications are running parallel? So the outcome of the resource allocation with the bandwidth and channel allocation, computation resource allocation at the server side and at the edge side, and then edge server selection based on what is the current situation or current computing and energy situation at those servers. Then more recently, we are looking at 3D reconstruction, which is real time. Now, 3D reconstruction is much, much complicated than object detection, because in 3D reconstruction, you have feature detection, then you have to do pairwise matching, then finally you have to do SFM, which is structure from motion, densify the entire cloud to get the actual reconstructed video. So it's very, very complicated. So you have to do position estimation, orientation, all these things come into play. We're talking about multiple cameras multiple cameras, and then you're moving. The cameras might be moving, the actual target might be moving as well, and that increases the complexity. So with moving cameras, moving object, different modality of the data, because you can deal with actual RGB cameras, depth sensors, sometimes LiDAR. So all these things create or make the computation more complex. Another challenge in this context is difficult to define real time. So what is real time? So are we talking about every frame real time, or are we talking about real time entire reconstruction? And that definition may depend on what kind of reconstruction it is. If it is one camera and the camera is moving, or we are talking about multiple cameras taking pictures at the same time. So definition of real time is very difficult to get from the community, from the literature. So maybe it depends on use cases. So we are trying to explore all these situations, like what is real time, what is close to real time, and what can we achieve in these scenarios. So a challenge, again, maybe I'll just brush through this part. So this is details about how the 3D construction is kind of challenging. So if the image is stationary, or the object is stationary, so you get the projection, and then if there is another camera, you just get the rotational component, you estimate the rotational component, then you find a fundamental matrix using that, and then you create this constraint, which is called epipolar constraint. So if the image is static, then the epipolar constraint equals to 0 kind of holds. Whereas if you have a moving object, then this epipolar constraint using the fundamental matrix doesn't really hold, because the object is moving, because the rotational component is much more complicated now. So in this case, for 3D reconstruction with multiple cameras, moving object, moving cameras, you have to consider different camera position, different image position, whatever object you are trying to capture, and then that leads to different fundamental matrix, and those fundamental matrices, you have to establish correlation between them because they are dynamically evolving. So the outcome of this is, if you have an original video like this, again, this is an image, it's a video. A video is not running for some reason. Again, has nothing to do with whether it is being remotely done or not. It's just the codec is going crazy. So anyway, so it doesn't really matter. So you have a video frame where these cars are supposed to move, and this frame is captured from a moving camera. So the detection result is something like this. So you have these detections, and then on top of that, you have these false positives where some stationary areas are also considered as moving objects. So that is the challenge of moving object detection, which is necessary for 3D reconstruction. Another problem that we see, so first is the challenge is in terms of the application, but also the challenge in terms of computation. So here we are running one of the most common multi-view stereo algorithms, which is OpenMPS. And when we run this on a pretty large or pretty considerable Amazon Web Service instance, we see that for high resolution, couple of stages, these are like 7 or 8 stages of the OpenMPS processing. So this densify point cloud takes 54 seconds. Refining the mesh takes 62 seconds. So we are talking about real time. This is no way close to this, is far from real time. If we bring down the resolution considerably, we still see like 6 seconds for refining the mesh and 28 seconds for densify point cloud. And if you go down in terms of resolution even more, then the outcome of the reconstruction is very pure, and it is better than, it is almost as bad as not having any reconstruction done. So, and another problem is these multi-view stereo algorithms are not really designed to exploit parallelism. So even if you use GPUs, you don't get a lot of improvement in terms of end-to-end time. So the challenge is in terms of computation time. The challenge is in terms of the computation itself. So what we propose for this case, again, this is just a paper that we are writing, and we are planning to submit it very soon. So what we are doing is we are doing some application side optimization and some system side optimization. So we cannot do just system side and leave the application the way it is. So that's why it's a collaboration between people who work in computer vision and people who work in systems and wireless networking. So at the application side, we are doing background subtraction. So it's very common, but in 3D context for real-time application is something new. So what we are doing is subtracting the background from the foreground. Foreground is something which might be moving more frequently, where background is something which is not changing a lot, which is more stationary. Can we separate these two, and can we run them at parallel? So that is the idea. So we are doing this blue part separately, hopefully at one particular server. This other part, which is foreground, which is moving, and where we have to run through the entire part, entire algorithm rather, that will be done as a separate server, and then they will be merged. So update and merge. That means update the foreground part more frequently, whereas the background part is not updated that frequently. Can it bring down the end-to-end time? So that is the exploration we are doing. And we are getting very interesting results. It's just that because it's not published yet, I can't really show the results at this moment. At the system side, we are doing instruction level parallelism, like running these sections in parallel, and then adding data level parallelism by different cameras or different sets of different time series data, running them at different servers. Can we do that? So system side instruction level parallelism, data level parallelism, and application side background subtraction and separating background from foreground. Then this is a very new work. It's just we are starting to explore. Again, all these projects are different components of building a smart disaster response, which is fog or mobile edge computing driven. So in this problem, we are looking at can we assume, or can we say that in future these applications or these smart disaster response applications or use cases will use dynamic spectrum access or opportunistically underutilized and unused license spectrum. In that case, how the spatiotemporal uncertainty of these available spectrum impact the real-time mission critical application. So that is something that we need to figure out. So there has to be a feasibility study, which we are planning to do in future. And then if you are asking the devices which are capturing, the end devices which are capturing the environment, they're capturing the video and getting all the data, if we ask them to do the sensing as well, so you have sensing, reporting, learning, decision making, as well as capturing the actual data like camera data. If we are combining all these things together, how that impacts the overall radio computation and energy resource management. So first stage is feasibility study. If that is something which is possible, then there is a question of whether we can do the resource management efficiently so that the applications are still real time. So this is the testbed capability we are building at Disarm Lab. So this is from the NSF grant. So at the device plane, we have some Kinect cameras, which are used for 3D reconstruction. We have smartphones, which are used for object detection, and we have some. We are actually buying some Mavic drones for moving cameras. And then at the wireless plane, we have the USRP devices, and then that kind of is acting as opportunistic access points. And then on-premise edge are being built with Jefferson TX2 GPUs and some Alienware Alienware laptops. So these are two different types of edge capabilities with different capacity and energy constraints. And then at the network edge plane, which is like the backend server, which is acting as a network edge. So the more you go down in the stack, the real time is more compromised. So can we do some optimization here using this test bed to kind of validate and evaluate some of the proposals that we are making. So this is kind of, I would say, 80% done in our lab, but because of the COVID and other stuff, it's difficult to manage everything from home. So hopefully by the end of next semester, the entire test bed will be ready to go. That's pretty much it. So thank you so much for your attention. And if you have any questions, please let me know. I'll be happy to answer. And before I leave, I cannot thank enough my PhD student Shaoji, my undergraduate student Amina and Elizabeth, Michael Leo from the FDNY Technology Office, and my collaborators at Temple University and Samsung. So thank you so much. Thank you.
Thank you, Dr. Debroy. And so here are several questions from the audience. The first question is that how do you define the edge in edge computing? Mobile device, base station, what else?
Fantastic question. Again, that's something that we have struggled ourselves. Like, what is edge? And if you ask different people, I have been asking this question in different conferences, Infocom, SEC, like what is edge? And I see in the same panel, I hear different opinions. So for me, so what I can say, for us, there are two definitions of edge. One is on-premise edge, which I think has the capability to give real-time response. If you're talking about network edge, I think that will incur more. I would say that is near real-time, but it won't be real-time. The first set of slides shows if it is network, it's going to network edge. Most of the applications and most of the test bed, like running things at the test bed level, like Cosmos and AirPo, these places, the first set of results that are coming through, they're saying we are looking at something around 10 milliseconds plus, which might not be real time. It might be real time for some applications, but not for all applications. So what we are trying to do here for disaster response is on-premise edge. So can we bring computation as close as possible? So kind of bring your own compute. So bring your own compute at a disaster scale. So can we do that? If we can do that, and if you have point-to-point communication between these edge servers and the disaster site, then maybe we can bring it down from 1 milliseconds to 5 milliseconds, which I think is what is needed for disaster response. But again, definition is, I can't say I have the definition, but this is how we define our edge. Sometimes people call it fog, which is, I'm okay with fog. This is just the semantics. But what we call it on-premise edge, which is different from network edge.
Thank you. So there's another question. Do you think it would be helpful if upload part of the data to edge, while not the whole data? How about the delay to upload data?
Exactly. I mean, this is exactly the result that we got in one of the first few slides that we showed. Like, it is better to sometimes do some little computation, because if you do some little compression, and we are just exploring, just scratching the surface here. But what we saw is like just compressing the data by itself and then uploading it to the edge does not impact the local device that much in terms of computation and energy, but considerably diminishes the total data that we are offloading at the edge. That means it drastically brings down the transmission cost from the device to the edge. So that has been our earlier, and actually this is exactly what kind of we concur with the assumption here. But again, there has to be more experiments done. Compression is just one part of it, but for complicated DAGs, can we do even more complicated stages at the device and then ask the device to offload the data? So again, it's like a optimization. Most of them are NP hard problems. So can we come with a heuristic which can achieve these? So that is the challenge. That is what hopefully we'll be able to achieve.
Okay, so again,
thank you. Questions are interesting. I didn't expect questions at 5 p.m. on a Friday. So thank you.
Okay, thanks for your presentation, answering question again.